Hi, so thanks a lot for having me. So yeah, I'm a climate scientist at the Carnegie Institution for Science at Stanford. And since I'm a scientist, I'm unable to give speeches and I can only talk in graphs and things. So I needed the PowerPoint. So you're gonna see some graphs. If you don't like graphs, I'm sorry about that. But so what I wanna talk about today is the leverage of the current moment in terms of the long-term trajectory of climate. So where do we stand right now in terms of the current moment? So the kind of iconic way in which global climate tends to be exemplified is through the global average surface temperature. So the temperature of the air about 2 meters above the surface. And contemporary global warming is typically thought of as the warming that we've seen since about 1950. And we are pretty much sure that all of this warming is due to increases in greenhouse gases, so nitrous oxide, methane, and in particular carbon dioxide from burning fossil fuels. And so, of course, we don't care necessarily about the global temperature itself. We care about impacts that this might have at the local level. So we've seen, this level of warming about 1 degree Celsius. You would multiply that by 1.8 to get Fahrenheit, if you're more comfortable with Fahrenheit. But about one degree Celsius has, in fact, translated into many relevant local impacts. So just to take an example that should be salient to a lot of people, U.S. Wildfires have increased over this time period. And we are quite certain that a portion of that is due to increases in the global average surface temperature, which is due to increases in greenhouse gases. So just to take an example from a recent study, this study concluded that 55% of the increase in fuel aridity, which is very important for forest fire intensity as well as area burned, was due to increases in greenhouse gases. And so depending on the extreme event, whether you're talking about droughts or floods or forest fires or hurricanes, you might get different numbers, and different studies will tell you different things, and us as scientists spend tens of thousands of words and dozens of figures trying to disentangle these things, and it's not always super straightforward. But what we do know is that this level of warming has indeed imprinted fingerprints and signals on all of these extreme events that I've mentioned. So where are we, what are our goals going forward? So on this same graph, if I plot the goals for the Paris Agreement, they are quite a bit above where we are right now. So this is the 2 degree limit, and then the goal to be 1.5 degrees above pre-industrial levels. And so you can see if we're seeing impacts here with this amount of warming, that's an additional essentially doubling of the amount of warming. And so that's not necessarily, it's not necessarily a one-to-one ratio in terms of impacts. Some impacts would increase more than the doubling, some might be less. But you can get a sense here that this is not necessarily, a safe limit if we're already experiencing negative impacts. And so one question that might come up is, okay, this is 1 degree Celsius. That doesn't seem like a whole lot of change in terms of temperature. So why are we seeing such dramatic impacts for just that? Well, we can get a better feel for this if we kind of zoom out a little bit in terms of, and get a longer picture in terms of what the climate change has done over a longer period of time. So this is zooming out to the year 1500, and I'll just put in here, here's the Industrial Revolution around 1800, and so it's no surprise that we've seen an increase in temperatures since greenhouse gases have been increasing in the atmosphere. We can zoom out to the year 500, and now we start to really see why we're getting major impacts over this recent time period. And it's because we are rapidly moving away from a global temperature that was relatively stable for a long period of time. And we can zoom out even further to 10,000 years ago. And this is an important time scale because this is what we call the Holocene, and this was basically the stable climate over the past 10,000 years in which human societies developed and materialized. And we don't think that's a coincidence. We think that we essentially were able to develop societies because we came into this relatively stable time period in climate. And so just to put on here about 8000 BCE is when the agricultural revolution occurred. And then, by 4,500 years ago, we have the Pyramid of Giza. And so by 4,500 years ago, you have major civilizations. And I think this is also important to think about in terms of moving forward, that, it can be very abstract to imagine societies even decades in advance or hundreds of years in advance or 1,000 years in advance. But we see the physical evidence of societies millennia ago. And so it should be kind of less abstract when you think about the past, that of course societies in the future will feel what we did today, and that will last for millennia into the future. And so I'll zoom out one last scale to 20,000 years ago. And I bring this up to show the last major climate change that occurred on Earth. This was the last ice age about 20,000 years ago. And the reason I bring this up is to show that, okay, on this scale, we're talking about 4 degrees Celsius, which doesn't sound like a whole lot. But that is the difference between essentially a mile of ice over all of Canada and the climate that we have today. So there was a mile of ice all the way down to over Boston by just 4 degrees Celsius colder than it is today. And so then you can start to see why the 1 degree of warming that we've seen so far has already had major impacts. So where are we going in the future? So here's a scenario where I put on here, this would previously be considered a pretty optimistic scenario, where humanity only emits about 625 gigatons of carbon. So this is a scenario where humans essentially draw down their emissions of greenhouse gases pretty rapidly over the next several decades. And you can see that even under this kind of, quote, optimistic scenario, we race extremely far out of the stable climate over the Holocene time period. And you can see that, this is several times the amount of warming that we've talked about in terms of the recent changes in extremes. And I've just plotted here kind of a central estimate, but we don't actually know very well exactly where that temperature would be. So there's a huge uncertainty on that. It might be less, and it could be actually a lot more. And the reason that it could be a lot more is that there's these positive feedbacks in the Earth system, or self-reinforcing feedbacks in the Earth system. So one would be clouds. So as it gets warmer, you can have a reduction in the amount of energy that's reflected back to space from clouds, and so that would cause further warming. And then there's other feedbacks that have to do with, for example, the carbon cycle, that as you warm up, it could be the case that more and more carbon is released from the land into the atmosphere and causes further warming. And so then that could push us even much further above in terms of temperature for any given amount of emissions that we emit. So that's kind of a more optimistic scenario. And this is what it looks like if we're talking about more of like a business as usual type scenario. So this is if humanity emits 2,500 gigatons of carbon. And you can see we're racing far outside of the stable climate of the Holocene. And of course, there'd be a very large uncertainty on this as well. This could be, in fact, much greater. But I'm showing it at this time scale again so that I can show you here, this is the ice age. This is the difference between a mile of ice over Boston and the current climate. And by the way, this is largely caused by changes in the Earth's orbit, so different than the current climate change causes. And that is essentially the difference that we're talking about in terms of, strong mitigation versus kind of a business as usual. Or if you prefer to look at it another way, about 7 times the current amount of warming that we've seen, where we're seeing these major impacts for example, forest fires. So one of the main themes here is I want to point out how much downstream into the future this also has effects. So this is imagining that essentially in both cases humanity stops emitting greenhouse gases by about 2200. But then what happens going forward into the future? So this is now 10,000 years into the future. And again, this is humanity has stopped emitting greenhouse gases, but still, under this business as usual scenario, temperature remains very much elevated, very much outside of the Holocene temperature range 10,000 years into the future. And even under the more optimistic scenario, you're talking about taking 5,000 years to get back into that range. And so this actually even looks kind of good, like at least, okay, temperature's coming back down. But of course, once you elevate temperature, you get other things moving in the climate system. And so we have things like the Antarctic ice sheet, which is another miles of ice on the South Pole, that once you raise temperatures and you get that melting, it's very difficult to get that to stop melting. So if I show you, instead of temperature, the exact same graph, but with sea level, which of course will go up as ice begins to melt, this is what sea level looks like. So sea level is continuing to increase in both of these scenarios. So here's temperature going back down, but the temperature is elevated, so sea level continues to increase. And the difference between these two scenarios, the relatively optimistic scenario and the business as usual scenario, is huge. It's about 65 feet of sea level. So that's, a 6-story building. And if you're talking about this more business as usual scenario, then this is, what the Bay Area looks like. So you have an inland sea in the Central Valley of California. And, this reshapes the coast of the United States. So this is the Gulf Coast, Florida, and the southeast United States. So we're talking about a ton of water here that is really, a huge magnitude change just from the difference right now between a kind of strong mitigation versus a business as usual type scenario. So I'm going to show one more graph here. So I've shown you temperature, I've shown you sea level, and now I'm just going to show on the exact same time scale emissions, the emissions of greenhouse gases into the atmosphere. So this is the flow of greenhouse gases from burning fossil fuels. So that's what emissions look like on this time scale. So 20,000 years ago, there's no emissions, there's no emissions, there's no emissions. There's industrial revolution, right? And we are here. So we start increasing emissions to about 40 gigatons of carbon a year right here. And so it's just a blink of an eye. So we are making a decision now between either dropping back down to zero very, very quickly, which still has very long-term consequences, or essentially waiting a few decades, allowing that to go back up, and then dropping down to zero. Because eventually, fossil fuels are not going to last forever anyway, so that's going to go to zero no matter what. But that decision, in the blink of an eye in terms of this time scale, has these huge downstream effects, and of course has very large effects in the very near future as well, given the impacts that we've seen recently. So I think this can be looked at as an opportunity. So if you kind of do a rough, 70-year division and say, okay, this is 300 years, 300 human lifetimes ago, and yet we are in this lifetime right now that we can make this huge impact on many human lifetimes into the future. And of course, it's even more intense than that, because there's, infrastructural inertia, for example, that if you decide to build a coal power plant versus a renewable energy source, that has downstream effects for decades, because a coal power plant's gonna be there for 30, 40 years. And so it's even more intense than a single lifetime. But our decisions right now have profound consequences, not only on the future, in the near future, but over thousands of years. And so that's the leverage of the current moment on the long-term trajectory of climate. Thanks.
Thank you so much, Patrick Brown. Running a little short on time, but we're going to catch up, no worries. We have 10 minutes to take your very best questions.
I would just comment briefly that in terms of drawing down emissions to zero, this is technically doable. I mean, we actually know how to do it essentially. And you know, the IPCC models this and the expense of it, and it's something like a few percent of GDP, while GDP is extrapolated to increase by like 7 times or something in the next century. So it's actually a very small fraction in terms of you know, total GDP or in terms of total expense. So it's a technically doable thing.
Right on. Hopeful. I'm a glass half full kind of person, so I like that optimism and can-do spirit.